Oxidation numbers, i.e. oxidation states, going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do DAT, OAT, and MCAT prep as well. I'll leave a link in the description where you can find those courses. Now, this lesson is part of my new general chemistry playlist, which I'm hopefully completing in the next month and a half or so. I'll be releasing several lessons a week throughout the rest of this school year, so if you want to be notified every time I post a new lesson, subscribe to the channel, click the bell notification. All right, so we're kicking this chapter off on oxidation reduction, electrochemistry. We just talked about oxidation numbers, and we learned some cursory rules for those in the way back in chapter 4, but we're going to get a little more robust set of rules here, not the typical ones you'd get in a textbook here, so a little bit different, a little bit easier to follow, truth be told. Before we get there, we just got to go back and remind ourselves what oxidation and reduction are. And so in a redox reaction, we are doing an electron transfer reaction. Electrons are transferred from one species to another, and so one species is going to lose electrons, one species is going to gain electrons, and truth be told, there are some complex redox reactions out there where you actually have more than one species losing or more than one species gaining, but at the very minimum, and most of the time, you're going to have one species losing electrons, one species gaining electrons. And we call the species that loses electrons, we say that it gets oxidized, so it experiences oxidation, and the species that gains electrons experiences reduction or gets reduced. So a couple little mnemonics here. We've got Leo the lion says grrr. So lose electrons oxidation, gain electrons reduction. That's my preferred mnemonic. So, but more commonly, you're going to see oil rig these days, but it's not my favorite because it doesn't have the letter E in it, which stands for electrons. But oxidation is loss of electrons. Reduction is gain of electrons. Now, it turns out we keep track of who gets oxidized and who gets reduced by looking at oxidation numbers, oxidation states. And that's why it's so important to be able to calculate these oxidation numbers. And that's really going to be the focus of this lesson, is calculating oxidation numbers. All right, so the way this works, we've got a set of rules here, and I've broken it up into 6 rules, and you're going to follow these rules in order until you've got one element left that you've not assigned. And once you get to that point, you just skip straight down to rule number 6, and that element has to be what it has to be to just balance out the overall charge. If it's a neutral compound, to balance it out to 0. If it's an ion, then to balance it out to whatever the ion's charge is. And so you're going to follow these rules in order. So the highest priority rules are at the top, and that's why those elements kind of get the priority and stuff. So rule number 1, elements in their elemental form are in the 0 oxidation state. So if you have an element rather than a compound, well, elements in their elemental forms are just in the 0 oxidation state. So I've got some examples here. So here I've got a couple of diatomics. So I very well could have put like sodium metal in here or something like that. So any element in its elemental form, not as an ion, but it's an elemental form, is automatically by default in its 0 oxidation state. Same thing here. This is ozone. It's not the standard state for oxygen, but it's another allotrope and is also considered an elemental form and in the 0 oxidation state. So if all you see is one element listed and there's no charge on the upper right, that is something in its elemental form and is in the 0 oxidation state. All right, so the next 2 examples both have 2 elements each, and when you've got a compound with 2 elements in it, the question is really which one's going to get assigned first, because the second one is just going to be then left to balance things out. And so turns out the first thing you want to look for in a compound is group 1 and group 2 metals. And notice I specifically say metals because group 1 hydrogen is in group 1, but it is not a group 1 metal. So you first want to identify group 1 or group 2 metals. And in a compound, group 1 metals are +1, group 2 metals are +2. And notice I have to say in a compound because if they're in their elemental form, well, then rule number 1 is going to tell us they're in the 0 oxidation state. But in a compound, group 1 metals are +1, group 2 metals are +2. And so if we look at magnesium chloride here, we do have a group 2 metal, magnesium. It's in the second column, the second group on the periodic table, group number 2, and is therefore +2 in a compound. And once we get here, we just skip right on down to rule number 6 because there's only one element left not assigned, and chlorine is just going to have to balance this out. Now, this is a compound, not an ion, and so being a compound, i.e. a neutral compound, it's going to balance out to 0. And so in this case, what would chlorine have to be so that when I add it to magnesium here, it's going to add up to 0? And I've got to factor in that there are 2 chlorines there. Well, each chlorine is going to be a total of -1. And so the oxidation state is defined per atom, and so each chlorine is -1. That is the oxidation state or oxidation number. And 2 times that -1 would get us a total of -2. And then we have one of these magnesiums, which is +2. And lo and behold, the total overall oxidation numbers add up to 0, just like they should for a compound. All right, so that's magnesium chloride. Magnesium is in the +2 oxidation state or oxidation number, and chlorine is -1. All right, moving on to hydrogen peroxide here. And hydrogen peroxide can be a little bit tricky. So most of the time we tell students, well, you have to know how to recognize a peroxide. A peroxide is when there's 2 O's, and we usually don't give you a better description than that. And unfortunately, like carbon dioxide has 2 O's, and it's not a peroxide. So peroxides usually have 2 oxygens and come with either a group 1 metal or hydrogen is the most common, but there's others as well. And so it's not the greatest steadfast rule. And so instead of having you be able to recognize when something is a peroxide and when it's not, we're just going to follow these rules. And rule number 1, any element, its elemental form is 0. Well, we don't have any elements in their elemental form. We have a compound. Group 1 metals are +1, group 2 metals are +2. We don't have any group 1 or group 2 metals. Again, hydrogen is in group 1, but it's not a metal. And so rule number 3 then deals with hydrogen. And hydrogen is +1 in a compound, except when it's bonded to only a metal. So if you see hydrogen with only a metal, and let me give you an example of that. So if I gave you something like sodium hydride, in which case, notice hydrogen is not even going to be listed first. Well, if hydrogen's with only a metal, not like a metal and some other elements, but only a metal like here, that's when hydrogen's going to end up being -1. However, you don't have to remember that, because if you followed the rules on sodium hydride, just be like, well, I'm going to assign the group 1 metal first as +1, and so hydrogen would just have to be -1 to balance. So it's not like you need to remember this. So, but hydrogen is going to be +1 unless it's with a metal only, and in which case you'd figure it out anyways from the rules. All right, so going back to hydrogen peroxide here, that tells us that hydrogen is going to get assigned before oxygen, and we're going to make him +1. And there's only one element left now, oxygen, so we skip all the way down to rule number 6, and oxygen's just going to have to be whatever it needs to be to balance this out. And again, this is a neutral compound, so it's got to balance out to 0, in which case oxygen's got to be -1. So we see that we've got 2 oxygens for a grand total of -2, and 2 hydrogens, therefore, for a grand total of +2. But just remember that oxidation number or oxidation state is always per atom. And so if you said that the oxidation state for hydrogen was +2, that's wrong. It's just +1. The oxidation number accordingly for oxygen, if you said it's -2, no, in this example for a peroxide, it's actually -1. So in most compounds, they're oxides. And for oxides, oxygen is in the -2 oxidation state. Peroxides are unusual in that respect. They're much, much, much less common. And oxygen's actually in the -1 oxidation state. But again, you didn't have to recognize that this was hydrogen peroxide and that it was a peroxide, and then remember that peroxides have oxygen in the -1 state. You just had to follow the rules I've provided here, and it works itself out. All right, the next 2 examples, again, each also have only 2 elements, and the question again becomes, who do you assign first? Well, with N2O4, we're going to look at rule number 1 and say any elements in their elemental form, and the minute you see you have a compound or atom element, you pretty much just skip right past rule number 1. Rule number 2, group 1 or group 2 metals, don't have any. Skip rule number 2 then. Rule number 3 deals with hydrogen. We don't have any hydrogen. Skip rule number 3. So then we move on to rule number 4, and this deals with transition elements. So in the middle of the periodic table, and we don't have, transition metals. We don't even have any metals, so we skip rule number 4. And then we go to rule number 5. And rule number 5 says the most electronegative element gets its typical oxidation state. And so what we mean by typical here, like the halogens are 1 electron short of being a noble gas, and so their typical oxidation state as an ion is -1. So oxygen's column on the periodic table, 2 electrons short of a noble gas, and their typical oxidation state as an ion is -2. Nitrogen's column -3. That's what we mean by typical oxidation state here. And so in this case, whoever's more electronegative, so they're like, I like electrons more, and I get to determine how many I have. Well, okay. And that in this case is oxygen. Recall that electronegativity increases as you go towards fluorine up and to the right on the periodic table, and oxygen's more electronegative, therefore, than nitrogen. And oxygen's like, I'm more electronegative, and so I get to decide that I'm -2, just like I like to be. And nitrogen's like, well, I can't do anything about that. And in this case, then nitrogen's the last element left, and we go to rule number 6, and nitrogen just has to balance this out. And so in this case, we can see that for the oxygens, we've got a total of -8. And so to balance that out, this is a neutral compound. The nitrogens are going to have to give us a total of +8. And there's 2 of them to spread that across, so each of them must be +4. And this can get a little bit confusing for students sometimes. And so the truth is, if you want to make this an algebra equation, you can. 2 times whatever nitrogen is plus 4 times whatever oxygen is has to add up to the overall charge. For a neutral compound, 0. For an ion, to whatever the ion's charge would be. But in this case, neutral compound, so it adds up to 0. And then if we substitute in that oxygen here has got that -2 charge, then we have 4 times -2 is -8. We'd add it to the other side to get +8, and we'd have 2 times whatever nitrogen is, adds up to 8. So nitrogen, once again, must be +4 for its oxidation state or oxidation number. So if you want to make an algebra equation out of it, you totally can. All right, KO2. If I want to give you a tricky example on an exam, KO2 is a fantastic, tricky example. Turns out is it even more rare than the peroxide. This is what we call a superoxide. And again, unless I give you a set of rules like this, asking students to remember when they have a superoxide would be even more ridiculous. So again, but if we just follow these rules, we're going to figure out that oxygen's in a funky oxidation state regardless. All right, so rule number 1 says any elements in their elemental form. Well, we got a compound, so that's going to totally not apply. We'll skip it. And then we look for group 1 and group 2 metals according to rule number 2, and we have a group 1 metal. So potassium here is a group 1 metal, and so has to be +1 according to rule number 2. And then we skip all the way down to rule number 6 because there's only one element left, oxygen, and he's just going to have to be whatever he has to be to balance this out. And this is a neutral compound, so we got to balance the overall charge out to 0. And so in this case, we've got that potassium again. We've only got one of them with a total charge of +1. And so the oxygens over here must have a total charge of -1 to balance it out to 0. But that -1 charge is split across 2 oxygens, which means individually they are each -1/2. So, and that is unusual. Seeing a fraction for an oxidation number, an oxidation state, super unusual, but that's what it turns out is indicative of a superoxide. It's oxygen in the -1/2 oxidation state. And it turns out that the superoxide ion is a polyatomic ion. It has 2 oxygens in it, and they share 1 extra electron. That way, on average, they're both in this -1/2 oxidation state. So I've really given you this example because I wanted you to see that every once in a while, it's unusual, but every once in a while you can have fractions as oxidation states. We'll see one more example of that here in just a second. Notice you also, again, could have made an algebra equation out of this. You could have said whatever potassium is plus 2 times whatever oxygen is adds up to 0. And then you would have substituted in that +1 for potassium. So you subtract it to the other side, and you would have had 2 times oxygen equals -1, and you divided by 2 and found out that oxygen is in the -1/2 oxidation state. All right, next 2 examples. So you got something else unusual here. So now we're not dealing with a binary compound, a compound with just 2 elements. Now we've got one with 4, and that's going to make this a little more complicated. But it works exactly the same way. You just follow the rules in order. Now again, rule number 1 deals with elements in their elemental form. So if these are all part of a compound, rule number 1 doesn't apply, and we skip it. Rule number 2, looking for group 1 and group 2 metals, and we have a group 1 metal in sodium. So he's going to be +1 in a compound here. Cool. Now, usually we'd got to this point, we're like, oh, there's only 1 element left. Well, we got 3 elements left, so we can't just skip to rule number 6 or anything. We just have to keep following the rules in order. So rule number 3 deals with hydrogen, and hydrogen's going to be +1. Now, the rule says that hydrogen is -1 when it's with a metal only. Well, there is a metal here, but it's not with a metal only. There's a couple other elements here as well. And again, hydrogen's going to be +1. And so we'll assign him now as well according to rule number 3. But we still have 2 elements left, so now we move on to rule number 4, and rule number 4 deals with transition elements. Well, we don't have any transition metals here, so we move right on to rule number 5, and we assign the more electronegative element. And oxygen's more electronegative than carbon, and oxygen's typical oxidation state is going to be -2. And now we've got 1 element left, and we only have rule number 6 left anyways, but even if we didn't, we'd jump down to rule number 6, and carbon is just going to have to be whatever carbon needs to be to balance out the overall oxidation states or oxidation numbers to a total of 0 yet again. So because in this case, once again, this is a neutral compound, oxidation states have to add up to 0. And so we can see here that sodium is +1, hydrogen, there's only one of those, and it's +1, but we got 3 oxygens for a total of -6. Again, they're each -2. The oxidation state is defined as -2, but it is a total of -6. And so we see here, what in the world is carbon going to have to be to make this balance out to 0? And there's just that one carbon. Well, we've got +2 over here, -6 over here. We need another +4. And because that +4 charge is on a single oxygen, that means that oxygen is in the +4 oxidation state. And that's how that works. And again, you could have made a big algebra equation out of this. Sodium plus hydrogen plus carbon plus 3 oxygens adds up to 0, and it would have worked out exactly the same. All right, another funky example here in NaN3 sodium azide, and we're going to see a fraction again here. And I just want to, again, give you one of those common examples that if I want to get tricky on the test and give you something with a fractional oxidation number, this is another one of those examples you might see. And so in this case, skip rule number 1, we have a compound, no elements in their elemental form. Don't skip rule number 2. Rule number 2, group 1 metals, +1. We've got one. So sodium, therefore, is going to be +1. And now we've got one element left, and we'll skip straight down to rule number 6. We don't have to know that this is sodium azide and that nitrogen's in some sort of crazy fraction oxidation state. The rules are going to figure it out for us. So we've got one sodium for a total of +1, and therefore to balance out to 0, since this is a neutral compound, then these guys have to add up to a total of -1. But there's 3 total nitrogens here adding up to -1, which means they are each in the -1/3 oxidation state. So once again, this is unusual, but what you've got here is the azide ion is a polyatomic ion. It has 3 nitrogens in it, and those 3 nitrogens share 1 extra electron total. That way, on average, they each have an extra -1/3 of an electron, and therefore are in the -1/3 oxidation state. All right, last example here. We're going to use one that's got a transition element here. So copper 2 sulfate here. So, and in this case, we've got a polyatomic ion, and this is the first time we've seen a polyatomic ion. And I want to write that polyatomic ion sulfate out separately here, so we'll see something. So, but let's just start with it in the context of the compound here, copper 2 sulfate. So rule number 1, elements in their elemental form, skip it. We have a compound, no elements in their elemental form. Rule number 2, group 1 or group 2 metals. We don't have any group 1 or group 2 metals. Rule number 3 deals with hydrogen. We don't have any hydrogen. Rule number 4 deals with a transition metal. And here's where you're going to get into some issues here. You have to remember the charges on your polyatomic ions. If you've forgotten them, go back and review them. So because you're going to figure out what the charge on a transition metal usually is based on what it's with, what anion it's with. And in this case, you have one copper with one sulfate. And if you don't remember that sulfate has a -2 overall charge as a polyatomic ion, then there's no way you're going to be able to figure out that copper here is in the +2 oxidation state. So, but that's the key. You got to remember your polyatomic ions. If you have a transition element with a polyatomic ion, you're going to have to know that polyatomic ion's charge to figure out the transition element's oxidation number. All right, we're still not done, though. We haven't assigned sulfur or oxygen, so we still got 2 elements left. So from rule number 4, we'll move down to rule number 5. And who's more electronegative, sulfur or oxygen? Well, oxygen is. And so he's going to get his typical oxidation state, once again, of -2. And so we've got 1 copper, which supplies a total charge of +2. We've got 4 oxygens that are -2 each for a total of -8 charge. And so what's sulfur going to have to be if this is all going to add up to 0? Well, in this case, it means we need a total charge of +6. And if that's really just on a single sulfur, that means sulfur is in the +6 oxidation state, or has an oxidation number of +6. Now, it turns out it doesn't matter if you have 1 sulfate or 2 sulfates in a compound, or if you just have the sulfate polyatomic ion all by itself. The oxidation states are going to be the same in any case, as long as we have sulfate as the polyatomic ion. But I want to see how it would work out if you did have it in the context of a polyatomic ion. And so in this case, if we were just assigning sulfur and oxygen here, we'd skip rule number 1, no elements in the elemental form, skip rule number 2, no group 1 or 2 metal, skip rule number 3, no hydrogen, skip rule number 4, no transition elements. Rule number 5, once again, oxygen's more electronegative, and so oxygen gets his typical -2 oxidation state. And then sulfur's just going to have to balance this out. But the key is with an ion, sulfur's not balancing this out to 0 anymore. It's balancing out to the total charge of -2. And we've got 4 oxygens that are -2 each for a grand total of -8. And so the question is, what do I have to add to -8 so that the overall charge comes out to -2? Well, that's going to have to be +6. So, and that's all on 1 sulfur, which means that the sulfur is in the +6 oxidation state. Exactly how it existed as copper in copper 2 sulfate here as well. So just wanted you to see it for an ion as well. And again, the overall charge does not add up to 0 in this case, but to the overall charge of the ion minus 2. Cool. And hopefully you've got some proficiency now in calculating oxidation numbers. So best way to learn these rules is just simply to work a bunch of examples. If you just simply try to memorize them, that's not terrible. But you'll find it's much easier if you just learn them in the context of working several examples. And again, this is probably a set of rules that you're not likely to have seen in your textbook and stuff like that. So my apologies if you don't find them anywhere else but right here. One thing to note as well, rule number 4 in dealing with transition elements. So the reason there is a rule number 4 like that is because transition elements can often take on multiple oxidation states, but you should know the 4 exceptions. So in a compound, aluminum is always +3, cadmium and zinc are always +2, and silver is always +1. But for all the rest of the transition elements, you'll have to figure out what they are based on what anion they're with, the same way we did for copper right here. Now, if you found this lesson helpful, a like and a comment, let me know, are pretty much the best things you can do to support the channel. If you're looking for any sort of practice involving electrochemistry and oxidation reduction reactions, or general chemistry in general, take a look at my General Chemistry Master Course. It includes over 1,200 practice questions. Free trial is available. I'll leave a link in the description. Happy studying.